Okay, look, I don't put a constraint for you. No, you should have this amount of pages. But in general, no, let's say if you are working two persons, no, not less than 30 pages. Okay? هلا,
Okay, thank you.
if you are finding that what you put is enough, it's fine if you do a lower number. It's not an issue. But try and to have information that is clear and enough to represent all aspects of your topic. So let's say if you are doing, if you are using double spacing,
Okay.
times the new Roman 14, okay, 30 pages is fine for two persons. Okay.
Okay, thank you.
Okay. Good afternoon. So today I will do a problem that is of high importance in energy, which is a problem on the process of which is happening in internal combustion engines. We'll try to relate a real application to what you learned in this chapter. Okay, so in this chapter we introduced for you the different laws of thermodynamics: zeroth law, first law, second law. We talked about energy forms. We talked about enthalpy, internal energy, work, heat, etc. So we'll try to illustrate these ideas, or the majority of these ideas, in a problem that is practical and that you face a lot in our daily life. And we'll see how we can use these theoretical equations to assess, for example, the efficiency of the process in an internal combustion engines. Okay. So to start with, I will talk in brief about what is internal combustion engine, how energy is, if you want, transformed from one form into other, and how I can use theoretical approach to assess the efficiency of my system. Okay. So to start with, let us talk in brief about what is. So here in this lecture, if you want, try to take notes, or if you want, you can watch it after and take notes. So it's like I have you in class and we're doing, I'm writing on the board. Okay. So we will deal with internal, we'll do a problem on internal combustion engine. This is a very interesting example of energy. You know why? Because we have transformation of energy in several forms. Do you think, yani, from the name, internal combustion energy, so the first form will be of which type? So first we'll have energy from transformed from which type of energy to which type? When we talk about combustion, okay, and the combustion process, what do we have first?
From chemical
Chemical
to
energy.
thermal.
Yes, very good, very good. So the first transformation here is from chemical energy. So through the combustion process, sorry, 1 second. So through the combustion process, we will have transformation of energy from chemical. We have transformation of energy from chemical form to heat form. Okay. And we can study this process through combustion equations. Okay. We can study how you have like bonds between molecules are if you want, changed in a way to form new molecules, and this will lead to release of energy, to release of heat. So from chemical form to heat form. And after this, after we transform the energy from chemical to heat form through the combustion process, what is the next step? So this is the first transformation we'll encounter in internal combustion engines. After this,
Mechanical motion.
exactly.
From heat to mechanical.
Yes, very good. So this, if you want, this heat energy will be transformed into mechanical energy through motion. Yani you will create a very high pressure and temperature, and these high pressure and temperatures inside your cylinder will push your piston and will lead to its motion. Okay, so two, we have the heat energy is transformed into mechanical energy. And in a first step, if we take in the conventional internal combustion engine, the piston will move, you know how, in which form? It will do translation. I will do for you a small picture to illustrate what is happening. So first, we transform this heat into an expulsion energy, a push on the piston, which will give it a translation motion. And this translation, so we'll go from one mechanical energy form to another. We have translation transformed into rotation of the crankshaft. Through a certain mechanism that will illustrate now. Okay, so here in this problem, we are having different forms of energy, and you are going from one form to the other until reaching the desired output, if you want. Okay, so translation transformed into rotational motion. If I want to, in brief, to do a small drawing, so what is happening is the following. You have here your cylinder, okay, and you have, of course, admission valves and exhaust valves that will allow you to control the introduction of the mixture first inside your cylinder. So first you introduce your air. In case it's you have gasoline and you have diesel, so we'll not go over these details, but let's say if you have a gasoline engine, you will introduce at the same time air and the combustible. You will, in this way, you will have a mixture of air and combustible within your cylinder, and you have a piston. You have first what we call the admission process. The piston will move down. Let's say we are talking about 4-stroke engine. So as the piston displays down, mixture is introduced into your cylinder. And after this, you will close your admission valve. The admission valve will close, so you cannot introduce air anymore, or air or combustible anymore. In the second step, your piston will move up and it will compress the mixture. Okay, the compression effect will create, if you want, increase in temperature and pressure of your mixture here. And when your piston is nearly close to the high level, to its maximum level, you produce, like here, a spark ignition to initiate combustion. Okay, and now the third phase is under the effect of combustion. You will have a very high increase into pressure and temperature within your mixture, and this, under the effect of very high pressure and temperature, your piston will be moved downward with a very high force. Okay, so this high push, which will lead to this translation, will allow to transform, if you want, the energy of combustion, which is in heat form, into a mechanical translation of your piston. And then your piston is related through a certain mechanism of a rod and a crank to your crankshaft. So you have your piston is connected to a rod and to a crank, and this is your crankshaft here. So due to force transmission through the rod, this will create a force here that will have two components. One that is, if you want, normal to your axis, it will passes by your axis, and another one that is tangent to your crank. Okay, and in this way you will able the tangent component of force will create a couple, and your crankshaft will rotate, and then the cycle will be repeated. Okay, so you have a cycle of 4 phases: admission, compression, combustion, expansion. And during the expansion process, you will use the combustion energy into, you will transform it into translation of your piston, and the translation of your piston will transmit forces through a mechanism. These forces will be decomposed into a normal and tangential component. The tangential one will be the one that is effective and will cause rotation of your crankshaft. So this is in summary the operation mode. Okay, now if you want to use the knowledge of chapter 2 to study the cycle, okay, we can try to draw its different phases and try to find, if you want, the efficiency of this cycle. Okay, so to start with, let me try to illustrate in a simple way the different phases in a graph. Okay, you have seen that one of the most important properties of a fluid, whenever I want to talk about energy, I need to define the state at a certain point, and the state at a certain point is defined by the temperature, the pressure, the internal energy, U. Okay, you have seen also other properties like enthalpy and entropy, and we'll see them into more details in future chapters. Okay, we'll see how we can use them into calculations in cycles. Now, if we want to simplify things here to see how we transformed the heat energy into a mechanical energy, okay, how we can see this in a plot of pressure versus volume. Let us try to illustrate the different processes. Okay, first, you have seen also in chapter 2 that we have different types of processes. Some processes we call them adiabatic. When we say adiabatic process, there is no heat transfer during this process. You have others that are called isentropic, where you have constant entropy. So when we talk about adiabatic and isentropic, this means that they are reversible also. So when you have constant entropy, this means you have reversibility of your processes. While if you remember, when in the chapter we talked about the third law of thermodynamics, for irreversible flows, delta S, the change of entropy, is positive. Okay. Now, how can we use these definitions here? How they can help us? Hello. For the internal combustion process, we said we have 4 phases. Okay. Now, here we can model these phases. Of course, you are not responsible of knowing if you want of doing this model, because this model requires experiments, requires observation of the realistic processes and doing some assumptions to have a modeling technique. But for example, how can I give it for you as a problem in an exam? In an exam, I can tell you, I will give you the cycle in a PV diagram, and I will tell you, try to, for example, knowing these parameters, try to get the efficiency of your system. For example, this is one possible scenario. Okay, so if I want to draw it for you, I already explained for you the steps, and now we'll draw them together. We said that first, let's say, in an internal combustion engine, whenever you close your admission valve, okay, of course, because you have admission and exhaust, the fluid that is circulating within your cylinder is not of constant mass. You have changing mass, because when you open, let's say, the admission valve, okay, you have air entering, or air and combustible entering your cylinder, and then when the admission is done, you close it. So now you deal with a certain mass that will be constant for a certain phase until you have start of exhaust, because after your combustion you need to exhaust gases. Okay, so the mass in your system is not constant, but one of the possible ways to model your system in a more simplified manner is to consider that the mass is circulating in my cylinder is not varying, but it's undergoing changes in pressure and volume. Okay, so let us say that we don't consider the exchange processes, admission and exhaust. We consider that my piston is now at the lowest point, and now I want to start to compress my mixture. Okay, because we said before combustion we should compress our mixture, and as the piston is moving upward, what will happen? The volume of air is decreasing, so you are compressing air inside your cylinder, and the pressure is increasing. So we can say that during compression we have this curve of decreasing volume and increase in pressure. So this curve here represents the compression stage. Okay, now I will tell you, for example, if I want to give a problem in an exam, I will tell you, assume that the compression is in adiabatic process. But when I tell you it's adiabatic, you should know what conclusions you can make, because we said that whenever we have an adiabatic process, then we don't have heat exchange. Okay, so we neglect during compression any exchange of heat between the mixture inside and the surfaces of cylinders. Of course, in reality it might not be very accurate, because always you will have some losses. Okay, sometimes at the end of combustion your surfaces of the cylinder are of very high temperature, so at a certain stage heat transfer will go from the surfaces towards the mixture, and as you compress and you increase your temperature, you will reach a stage where heat will be transferred from the mixture towards the surfaces. Okay, but this process, if you observe it, you might find that if I model it as adiabatic, this will not affect a lot my results, so I can use it as an assumption that my compression is adiabatic. Okay, and always to see if a model is working or not, you make assumptions, but then you can verify them. You do your calculation and you compare with experiments. If you obtain the closed results, this means that the simplified assumptions you did were helpful to do a theoretical calculation, and at the end give you an approximate idea about the real process. Okay, now if you want after to enhance your predictions, we have a lot of tools. If you want to, we call them sometimes correction factors. You can implement correction factors to have closer results between reality and theory. Okay, so now let us assume that the compression is an adiabatic process. Then we said when the piston is very close to its highest level, we can give a spark, and the spark will initiate combustion. Okay, now we know, of course, that combustion is very fast. Because combustion is fast, especially in gasoline engines, we can model it as a process that is instantaneous. So it's taking place at constant volume, but with a very high increase in pressure. Okay, so at the instant I give the spark, of course it will need some time to have inflammation, but if we neglect this time delay and we consider the combustion process as instantaneous, we can model it as a constant volume process. Okay, and with a high increase in pressure. So here this is a combustion process. Okay, and we model it as an isobaric process. When we say isobaric process, sorry, isochore. Isobaric is constant pressure. Isochore is constant volume. Okay, so we model it as constant volume process. Now, after the combustion, what will happen is that this energy, this combustion energy in form of heat will lead to very high, as we can see in the figure, will lead to very high increase in pressure. And this is also, this will happen with, of course, increase in temperature. So what will happen now is that this mixture of very high pressure and temperature will have a push on the piston. It will push it downward with a very high force, and we'll have now what we call the expansion process. Due to this push, the piston will move down, and in this phase, I can extract the energy and transform it from a heat energy to an energy of motion in translation mode. Okay, so now during this expansion, we call it expansion process. Okay, also here, one good assumption is to say that I will model the expansion process also as an adiabatic process. Okay, again, I tell you, you don't have to make these assumptions, of course. These assumptions will be given for you, but you should be able, if I give you details, if I tell you, consider the compression adiabatic, consider the combustion instantaneous at constant volume, consider the expansion adiabatic, should be able to draw the graph and to do the analysis of the graph in order to see how your energy is transformed from heat to work and how you can calculate the efficiency of such system. Okay, and finally, the final phase, okay, if you want, this phase will replace the exchange of gases, because in reality, what you do in real cases, you don't circulate the same fluid within your system. No, you exhaust products of combustion, which will be characterized by a high temperature, and you introduce instead of them a new charge, new air that is at lower temperature. So if you want to avoid modeling these complex phases of admission and exhaust while keeping the physics, you can consider that the exchange of gases can be modeled through a process where you have heat transfer from your system to the environment. So you have heat rejection. Why you should have heat rejection here? Because you are exhausting your product of combustions which are at high temperature and replace them in your cylinder by fresh air at a relatively low temperature. So this exchange of gases can be modeled as a constant volume process where heat is rejected. Okay, so now I have 4 phases, and I have 2 of them are adiabatic, compression and expansion, and I have the combustion process at constant volume, during which I am introducing heat to my system. So during the combustion process, I gain heat. During the exchange of gases process, I have heat rejection. I lose heat. And then what will be my network? If I want to calculate the network during my cycle, which formula can I use? According to your knowledge of this chapter, which balance allows me to calculate the work done by a certain machine, knowing the fluxes of heat? Do you remember which law we can use?
Is it the first law of thermodynamics?
Exactly. It's the first law of thermodynamics. The first law of thermodynamics states the following. Can you remind me, please? What is the first law of thermodynamics? Who can
I
tell me?
think it was the total energy in
Yeah,
minus
exactly. Sum of Q dot in, okay, minus sum of Q dot out equals to what? Equal to the net work, okay, equals to W net, which is the net work done by my system. Okay, now please, I talked also in this chapter about sign convention. Please pay attention for sign convention. Okay, this means that you have several conventions for the signs. In some books, they write the first law in the following way. Okay, they write it as sum of Q dot, okay, plus sum of W dot should be equal to 0. Okay, if they use this convention, okay, this means that all rates of energy and work coming in are counted as positive, and all the rates getting out of your system is counted as negative. Okay, هلا هي in reality, if you want, this term is derivative of energy with respect to time. Yani how energy is varying with time. But in steady applications, you don't have a transient storage term. So if you remember, the law in its first state is that the transient storage of energy is equal to sum of fluxes in minus sum of fluxes out. But when we deal with a steady application where you don't have transient storage, this will be equal to 0. So for example, whenever they tell you it's a steady process, then the balance will equal to 0. So if you take a system, you have all fluxes coming in, summation of all fluxes coming in of energy, and these fluxes can be in heat form or in work form. Okay, should be equal to fluxes, sum of fluxes getting out. Now, in case we use this convention, which is to do the summation, then we consider that any work that we put on a system is positive, and any work produced by a system is negative. Then we put the positive sign, because always, whenever you do the balance at the end, every flux in should be accounted at the end as an added value of energy, and every flux getting out should be accounted as a negative value. Okay, now how we play with conventions, we consider sometimes, some books say that a work, to consider that a system has a positive work, so it's producing work, it should give work to the environment, to the outer environment. So we consider then in this convention for us, every work rate produced by the system is positive, and every work rate done on the system is negative. This is a convention used because we consider that a system to be to have if you want a certain efficiency or production rate, it should deliver work. This is a way of thinking. And if I deliver work to the outer environment, I am producing energy. I count it as a positive energy because I'm giving a work to the external environment. While if to operate my system, I need to put work on it, I count it as negative. If I want to use this convention, I cannot say that sum of Q dot plus sum of W dot equals 0. No, I should say sum of Q dot minus sum of W dot equals 0. Why? Because in this case, my work that is going out is considered positive, while the work that is coming in is considered negative. But in a balance of energy for a system, all fluxes that are added to the system will increase its energy, and all fluxes getting out of the system will decrease its energy. So I should be aware of the convention I'm considering. Okay, whenever I use the easiest convention is everything coming in is plus, everything getting out is minus. Then I write sum of q dot plus sum of w dot equal to the variation of energy with time. And if it's a steady application, it's equal to 0. While if I use the other convention, if I consider the work output as positive, then I should put some q dot minus some w dot equals 0. You are free to use the conventions that you want, but you should understand it and know how to apply it. Okay, so here when I put some q dot n minus some q dot out equal w dot net, I used the second convention because I had it minus sum of w equals 0. And when I took this term to the other side of the balance, it is w dot net. And here, w dot net will represent the produced work of my system. And we know that in an internal combustion engine, we transform heat into work. So w dot net will represent physically here the work that is delivered by your system, by your piston cylinder system to your crankshaft. Okay, so this is the basic equation I will start from in order to calculate the efficiency of my internal combustion engine. Okay, so I will say sum of q dot, and then everything in is plus, everything out is minus, equal to w dot net. Okay, now let us again draw the cycle and determine at which stage we gain heat, at which stage we reject heat, and at which stages we have production of work, and at which stages we need work. We need to put work on our system. Going back to our cycle. So as we said, it's the PV. Let us go phase by phase, okay? In the compression, in the adiabatic compression part, we said it's adiabatic. Do we have any heat exchange during this phase?
No.
No. So let us call points A at the beginning of compression, C and no heat here. Do you think that in compression we should put work on the system or we will gain work?
We will put work.
Exactly. We will put work. Why? Because we need to put a certain work to move the piston upward. Okay, so W compression is a work that we put on the system. But you know why you don't have to have a source for it? يعني مش ما حتكون external source. You know why? Because you will use part of the work produced by expansion to do the compression work, the compression part. And what I mean by this, when you operate your cycle, okay, this cycle will be continuous. So you will have continuous motion of your crankshaft. It will continuously rotate. So during expansion, you will give it the required push to rotate, and you will give it, if you want, enough energy that will allow us to complete its rotation. So when it's doing the other half of rotation, if you want, it will a part of this energy will be given to compress your air through the upward motion of your piston. Okay, so if you want, this is why when we talk about W net, we consider that a part of the expansion work that is delivered, that is an output for me, it's produced by my system, a part for it will be used to move my piston up during compression. Okay, so in this phase we put work, it's the compression work. Now during combustion takes place at constant volume. Do you have a work produced during the step, during combustion, or just you
No.
have heat?
Just heat.
Okay, if we physically, if we think in a logic way, you have heat that will enter your system due to combustion. Now, to know why we don't have work, try to remember some formulas related to work. You remember for work, what was the formula for a certain process?
It was P times delta V because there's no change in volume, so it's zero, so work is
Very
zero.
good, very good. If you go back to this chapter, one of the formulas for work is integral PDV. Okay, and since your volume is not changing here, this means that dV is zero, no change in volume. So the work from this point to this one is zero because I don't have any change in volume. And then I only have during the step a Q end, Q dot end. Okay. So we put the dot symbol for a rate. So this means variation of energy with time. So we have a flux of energy that is coming in due to energy produced by the combustion process. Okay. Now, in the expansion phase, I will have what? Here I will have production of work. So I will have W dot expansion. And of course, W dot expansion will be much larger than W dot compression. Of course, this is logical, but how can I graphically demonstrate this? You remember how I can do graphical interpretation of work?
Was it the area under the curve?
Very good. If you go back to this definition, the work is integral PDV. Mathematically, when you do integral of a function with respect to a variable, this represents graphically the area limited between the curve and the graph. So let us use another color. Okay. You have here during the compression, okay, the area between the pressure curve and the axis V represent this area, represent integral PDV. So mathematically, the compression work is equal to this area in green. Okay, so this is integral PDV for during compression phase. Now, during the expansion phase, this is your graph, okay, versus V. So you can detect a larger area. So the area limited by your upper curve and V will represent for you the produced work. And the net work will be the difference between these two areas. So the network, if you look at this figure, will be limited by your graph. So this is the network. The network is computed as the area of your cycle curve, of your closed curve. Okay, so the area in red will represent W net. Okay. Yeah, so we'll open another meeting to continue.